Let's say we have a test set of 15 chest x-rays, which we ran through our model to get an output probability or a score for each of them. We can plot these 15 output scores on a number line between 0 and 1. Now, some of these x-rays will have a ground truth of disease and some will be normal, so let's color them accordingly. Here, disease is red and normal is blue. We can pick a threshold small t that sets everything on the right of the threshold as we classify positive, and everything on the left of the threshold we classify as negative. Now notice we can compute the sensitivity and specificity of the model. Here, the denominator for sensitivity is the total number of disease examples, which we can count as the total number of red, which is going to be 7. The numerator is how many of those are positive, or in other words, on the right side of the threshold. This is all of them except 1, which is 6. So our sensitivity is 6 over 7, or 0.85. Similarly, the denominator for specificity is the total number of normal examples, which is the total number of blue circles here, which is 8. The numerator is how many of those are negative, or in other words, on the left side of the threshold. This is all except 2, so this is 6. So our specificity is 6 over 8, or 0.75. Let's say we now change the threshold such that it was higher. We now expect we classify fewer examples as positive and more examples as negative. We can now recompute the sensitivity and specificity. Note that the sensitivity has gone down, our numerator has fallen, and the specificity has gone up, our numerator has increased, because we're now correctly classifying more normal patients and incorrectly classifying more diseased patients. We can take this to the extreme and set the threshold to be at 1. In this case, sensitivity is going to be 0 since no examples are classified positive, and specificity is going to be 1 since all the examples are classified as negative.